Part 2 of the slides on radioactivity. So we have gone through different types of radioactive decay and deionization and all of that kind of stuff. There's the alarm, all right, and how they work and how dangerous they are. Let's talk about how long they last. So we talk about how long it takes for elements to fall apart based on their half-life. The half-life is defined as the amount of time, we write this on the whiteboard, okay? Half-life is called the T1 half. And it's the amount of time for half of the atoms to disintegrate. Disintegrate, excuse me. So in other words, if I had 5 grams, I go down to 2.5 grams, that is a half-life. And then if I go down to another 1.25, that would be a half-life. All right, so let's go back to here. So you can see, right, if I had 10 grams, 5 grams is a half-life, another down to 2.5 is another half-life. And just different elements have different stability, so that some elements take longer to fall apart than others. These are just some examples of half-lives and how they decay. So carbon-14 you may have heard of, beta decay, it's about 6,000 years. Potassium-40, a billion years. That's 700 million years. Okay. Some synthetic ones, I-131, 0.022 years. So some of the, you'd have to do the math on how long that is. 28 years, 30 years, 24,000 years. So it just depends. Some are much more stable than others. Right? So uses of radioactivity, we take advantage of the fact that they give off energy and we can detect them. Interestingly, radioactivity, remember the physical and chemical properties of the elements are still there as well. So for example, carbon, all the reactions that regular carbon does, carbon-14 will do. All the reactions that regular iodine does, I-131 will do. And pick an element, they do the same physical and chemical properties, but just that they're radioactive, right? So carbon-14 dating is how we can tell how old fossils are, because it's got a half-life of almost 6,000 years. So remember, there's a carbon cycle. Carbon is in the atmosphere. It's picked up by plants, right? Animals eat plants. Then you exhale carbon dioxide, and it just goes around in a circle, right? And carbon-14 is just naturally formed. There's a lot of radioactivity in outside of the atmosphere, and neutrons bombard things. And anyway, it's naturally occurring. Right? Just we talked about background radiation. So this is carbon-14. And I just said this, they have the same physical and chemical properties. So there's a certain amount of carbon in every living thing, and the amount, because the carbon-14 percentage is always the same, when that living thing dies, it stops turning over carbon. And that means that, but the carbon-14 will fall apart. And so you can kind of tell by how much carbon-14 is left, then you can determine how long ago that organism died. So if you find a bone that has a radiation of 12, normally there's 16 radioactive units. Right, if there's 12, that means you have 3/4 of it left. You could calculate when it died from the following graph. It has to be something that was alive, though. Right, this is just a feel for it. Interestingly, I was up at Bristlecone Pines National Park, and the Bristlecone Pines are the oldest living things. And a scientist had taken a core from Bristlecone Pines, and like all trees, they put down a ring every year. And they actually recalibrated the half-life of carbon-14 using Bristlecone pines, or at least that's what the signs on the hike said, or in the little museum. Okay, I-131 is a radioactive isotope of iodine. So it has an 8-day half-life. So what this can do is, again, we can take advantage of the fact that we have ionizing radiation. So ionizing radiation, right, it gives off little things, which means it can kill cells. It gives off little particles. In this case, it's a beta emitter, and that can destroy cells. Well, cancer cells are rapidly dividing cells. And so if you can take radioactivity and focus it and just kill the cancer cells, then that would be a nice trick. So iodine is something that if you ingest it, it goes to your thyroid. Your thyroid likes it. And so that it's been used to treat a thyroid disease. It destroys the cells. Now again, it doesn't know the difference between healthy tissue and unhealthy tissue, but because cancer cells are rapidly dividing, they're much more susceptible. So any type of radiation treatment, the patient will get sick, but the idea is that the cancer would die first. This is a technetium is a radioactive tracer, and so it'll go where typically calcium goes, brain, thyroid, lungs, liver. Okay. These are just others, okay, synthesized into sugar and used for positron emission topography. Okay. Half-life is 100 minutes, so that's not even 2 hours. So in a day or so, it's gone easily. Okay, this is an example of a scan from PET scan. Okay. So the nucleus contains a huge amount of energy. So just giving off particles can expose film and things like that. But this energy can be used for a lot of things. So this is Einstein's famous equation. And just to give you a feel for this, this is the energy, this is the mass. C is the speed of light. The speed of light is 3 times 10 to the 8th. So if you square it, it's 9 times 10 to the 16th. I'm sorry, 9 times 10 to the 16th. So it's a huge amount, basically 10 to the 17th. So it's a small amount of matter releases a huge amount of energy. That's that nuclear force we were talking about. Right? So that can be used. It's obviously been used in weaponry. We talked before about nuclear power plants, so let's look at how a nuclear power plant works. When we went through energy, the nuclear power plant idea was discussed that radioactivity gives off heat, which is used to heat water, and that's true. But now we can look at exactly how that works. Right? So typically, we use heavy nuclei like U-235, polonium-239, bombarded with neutrons. This generates a lot of energy and heat. And when people are looking at radioactivity, they say they use centrifuges. What the centrifuges do is they can separate things by mass. So uranium has 2 major isotopes, 238 and 235. 235 is the one that's used. And you take just regular uranium, which is from a rock, dug out of the ground, and you put it in a high-speed centrifuge, and you can separate the isotopes based on their mass. Right, so this is in general how a nuclear power plant works. So the fuel rods right here, okay, these fuel rods are radioactive. These are the source of radioactivity. This is inside of a very thick vessel, right? And what these are doing, they're spitting out neutrons and ionizing, falling apart, and all this energy is in here. These control rods are porous things that absorb some of the neutrons so we don't get a chain reaction. And by moving these in and out, you can control the rate of the reaction. If all of these are gone, this reaction can become a runaway. Right? And then what happens is the heat comes out here, goes into water, heats water, turns turbines. Right? So anyway, and again, when these control rods are spent, they can't be used for radioactivity. They're still radioactive. I'm sorry, they can't be used for fuel, meaning they're not giving off enough energy to use fuel, but they're still radioactive and they can still be ionizing. And if you look at what's going on in San Onofre, they're dismantling that power plant, and it's going to take a long time. Okay, weapons, of course, enrich uranium and polonium, and in this case, you don't have control rods, so you get a runaway reaction. Fusion would be nice. That was in the Spider-Man movie with Octavius. The idea is using the chemistry of the sun, right? And we talked about plasma a long time ago. The problem is the sun's very hot. So if we could do fusion, it would be very clean, but no one's ever been able to do it at temperatures that we can control. In other words, it has to be very, very hot, and then you can't use it because you just can't deal with that much heat. But this is how it works. So hydrogen fuses into helium, right? So you get hydrogen fusing to make helium. I'm sorry, helium nucleus, a hydrogen with a deuterium. Then a hydrogen and a deuterium make a helium-3. And this is energy that can be used. And then we get another helium and 2 hydrogens. Right, that's it for the slides. So you should now be able to do